we'll talk about addition of angular momentum. But before I proceed, let me just recall some results of last class. So recall that we had for an angular momentum problem, we have L square and L3 as a complete set of compatible observables, and we are looking at it in terms of the common eigenstates. So we denoted them as Lm, and L square operator, when it acts on this, there is an eigenvalue which is given by h bar square L into L plus 1. So this Lm is an eigenstate of both L square and L3. H bar m Lm. Okay, so this is what we have seen, and for orbital angular momentum, this L will take values 0, 1, 2, etc. And for a given L, M will take values from minus L up to plus L. Okay, so this is what we have seen, and further we have noticed that you can define something called ladder operators, L plus minus, which are defined by using L1 plus minus IL2. Okay, and such that when L plus acts on some L comma M, it will be some constant C plus, which I think I did not evaluate last time, L M plus 1. And you can see that this L plus minus will be M plus minus 1. So the first task is today we will evaluate this C plus minus. Okay, so let us evaluate. These are constants, and we should know those constants. So let's say first let's talk about L plus acting on L comma M is equal to C plus acting C plus times L plus M plus 1. This is what is our, and remember this Lm, whatever is L and M, they are all normalized states. So now let's try to take an inner product of this with itself. Then this is like a particular state. So you take the inner product of that state. Okay, so that will be L M, and the dagger of L plus is L minus. This is if this is a ket vector, and corresponding bra vector will be like this. And then take the inner product of this with respect to L comma M, and that is equal to, you will have C plus modulus square, because when you take inner product of right hand side, it will be C plus star, and then your L m plus 1, L m plus 1. So this is 1, and we have to of course find out this, and I think last time we had evaluated this. So your L minus into L plus, okay, so that is equal to L1 minus IL2 into L1 plus IL2. So that is equal to L1 square plus L2 square plus I times the commutator of L1 comma L2. Because L1 L2 is with plus sign and L2 L1 is with minus sign, and this can be written as L square minus L3 square, that is L1 square plus L2 square, plus L1 L2 commutator is IH bar L3. So you will have minus H bar. So if I substitute that one here, so we have C plus modulus square is equal to L m, and here you have L square minus L3 square minus H bar L3. This is the operator Lm. And remember that this Lm is simultaneous eigenstate, the common eigenstate of L3 and L3 L square, and hence you will get this will be equal to H bar square L into L plus 1 minus H bar square M square minus H bar square M. So this factor into the inner product of Lm with Lm, which is equal to 1. So you get C plus as H bar square root of L into L plus 1 minus M into M plus 1. Okay, so this is the coefficient for this one. So we can write down this particular equation with this coefficient. Okay, so now let's say that you are interested in asking what happens for L minus. So let's say you ask what is L minus acting on L comma M is equal to P minus L comma M minus. So I will write this little directly. This will be equal to H bar square L into L plus 1, this factor will remain same, minus H bar square M square, that will remain same, but here you will have plus H bar square M. Okay, so because of this, what happens, your this will be equal to C minus will be equal to H bar square root of L into L plus 1 minus M into M minus 1. Okay, so as a result, we can write this L plus minus acting on L comma M is equal to H bar and square root of L into L plus 1 minus M into M plus minus 1. So this is the coefficient, and L M plus minus 1. So this is the action of the ladder operators on the common eigenstates of L square and L3. Okay, so this is one thing which I think we did not do it last time. So let me complete that. Okay, so the second thing is if we have spin, okay, so that is if we have spin angular momentum or total angular momentum. Total angular momentum is basically sum of spin and orbital angular momentum. Then we generally represent as angular momentum J square and J3 as CSEO. Okay, and you represent J comma M as your eigenstates. Okay, and J will take values 0, 1 by 2, 1, 3 by 2, and so on. So when you have spin or total angular momentum, you will have both integers and half integers. This we had seen last time, that this is the general result, but because of certain classical nature of the orbital angular momentum has given us this result that only integer values are there for the angular. In general, you will have both integers and half integers. Okay. Now what we are going to look at is addition of angular momentum. That means, let's say that we have, so let J1, okay, this is a vector, and J2 be two angular momentum. Okay, so you can think of, I am now trying to be very general. These both can be orbital angular momentum. One is orbital, one is spin, or both can be spin, or both can be total angular momentum also. So this is, so my analysis is very general here. So let J1 and J2 be two angular momenta. Then the total angular momentum which I will call it as capital J, is vector sum of J1 and J2. J1 vector plus J2 vector. Okay, so I don't want you to get confused with components. These are not components. These are just what is called this is angular momentum 1. This is angular momentum 2. Okay, so it could be that your J1 and J2. Okay, so both can be L1 and L2. Okay, so these are both angular momentum are L and S, are S1, S2, or J1, J2. Okay, so these are possibilities. It could be any of these possibilities. Okay, so now let's try to look at the structure of the state space. So so if you look at for angular momentum J1, okay, we have J1 comma M1 as the set of states, okay, as the basis. Okay, and for a given J1 as the basis, and so the number of such vectors, okay, so a number of such kits is equal to 2J1 plus 1, okay, as the basis of 2J1 plus 1 dimensional Hilbert space. Because M1 will take values from minus J1 to plus J1. On the other hand, for J2, we have this basis J2 comma M2 as the basis of 2J2 plus 1 dimensional Hilbert space. These are finite dimensional Hilbert spaces, but once you fix your J1 and J2, these are the. Now for the composite system, okay. Now for the composite system, of the total angular momentum, composite system of total angular momentum. The Hilbert space is we call it as a tensor product of the two Hilbert spaces. Okay, so if I call this Hilbert space as H1, and if I call this Hilbert space as H2, okay, then this H is basically written as this H1. This is called tensor product or direct product of H2. So the dimension of H, the dimension of the composite Hilbert space is equal to 2J1 plus 1 into 2J2 plus 2 plus 1. So this is the dimension of this Hilbert space. Now you can say that so you can talk about basis of this composite Hilbert space. Okay. So so for this problem, we have J1 square J2 square. Let me now write it as J1Z and J2Z because I am now saying, let me write it as Z here, not to get confused with this 1 and 2 corresponding to two different angular momenta. So we have this as CSCO because all these operators commute among themselves. J1 square, J2 square, J1Z and J2Z. Okay, so the common eigenstates. The common eigenstates.
இது 3000 CPM வந்து எந்த இடத்துல வருது பாத்தீங்க ஸ்வைப் எடுத்து பாத்தீங்க
Common eigenstates of these four operators are it is J1, J2, M1, comma M2. Okay, so M1 will go from minus J1 to plus J1, M2 will go from minus J2 to plus J1. Okay, so this forms and this forms a complete orthonormal basis for H. Okay, so that is fine, but it turns out that equivalently we can have J1 square, J2 square, J square and Jz, where J is the total angular momentum, as CSCO. That means these four operators also commute among themselves, which implies that so you can have J1, J2, capital J, comma M is another complete orthonormal basis of H. Okay, this is another complete orthonormal basis of H. So we have now two bases. Okay. So let us call this as basis 1 and let's call this as basis 2. Okay, so now we can ask a question that we will be able to, so it is possible that possible to express every element of basis 2 as a linear superposition of elements of basis 1. This is easy to understand because an element of basis 2 is in general a vector in H, and every vector in H can be expressed as elements of basis 1 because that is a basis. Okay, so that means I can write down that my J1, comma J2, comma J, comma M, okay, that is equal to, so here I have sum over, okay, so I can say that some coefficient. Okay, so let me come back to this coefficients. J1 prime, J2 prime, M1, M2, okay, and now the summation is on J1 prime, J2 prime, M1 comma M2, and of course this C depends on J1, J2, Jm, and J1 prime, J2 prime, M1, M2. Okay, so it depends on all these factors. Okay, so this particular coefficient is called Clebsch Gordon coefficients. Clebsch Gordon coefficient. These are called Clebsch Gordon coefficients. Now, if you find out, you can find out these coefficients. Once you find out these coefficients, you will be able to go back and forth from basis 1 to basis 2. Now, it turns out that finding these coefficients is one of the very important exercise in quantum mechanics. Also in various applications where you use quantum mechanics, for example, in particle physics or nuclear physics. These kind of coefficients are very, very important in many applications. Now, what is the way to find out these coefficients? Okay, so let me first say that okay, so I forgot one thing. Okay, yeah, that's fine. Now let me just so we have to find out these coefficients. Okay, so these coefficients need to be determined. Now let's try to understand this addition of angular momentum in terms of the values of the capital J. So we ask a question, given J1 and J2 as quantum numbers Okay, quantum numbers of two subsystems. Okay, then what values does J take? And J is the quantum number of the, so where J is the quantum number of total angular. Okay, so this question we can ask. Now it turns out that, see, this is a vector addition, as I have shown you that. So since your capital J is equal to J1 plus J2, okay, so you can see that imagine J1 and J2 are two vectors. Okay, so it is something like this. Let's say you have a vector J1 and J2 can be actually added to J1, so that this becomes, if the angle between them is 0 and they are added, then you are going to have J1 plus J2. Okay, or you can also say that you have J1 and then you have J2, which you add in the opposite direction. Then it will be like J1 minus J2. Okay, but then this could be large or this could be small. Okay, so this is one possibility. Other possibility is that you have J1 like this and J2 like this. Okay, so in any case, you have, in that case, this is J2 minus J1. Correct. So the values of J, the possible values of J will be J1 minus J2 modulus up to J1 plus J2 in units of 1. That means J1 minus J2, J1 minus J2 plus 1, etc., etc., up to J1 plus J2. So these many values that J can take. Now you can see that if you are, for example, let's take some simple examples. So, for example, let's take J1 is equal to half and J2 is equal to half. Suppose we have two, like let's say two spins, both are half half. Then what happens? Your J can take values half minus half modulus.
Sir,
Yes.
sir, sir, this J equal to J1 minus 2 to J1 plus 2. This values means, sir, this is not the eigenvalue of J, right? Or
this is not the eigenvalue. This is basically the quantum number.
okay,
Okay, so this is the quantum number. That means it is related to eigenvalue. For example, when you are taking J square, so the eigenvalue of J square will be h bar square into J plus 1. So it is the value of that quantum number that is given from J1 minus J2 modulus to J1 plus J2 modulus.
yes, sir. Yes, sir. Thank you, sir.
So this is 2 half plus half. Now this is simply, you have only two values, that is 0 and 1. So j can take values 0 and 1. Now look at this expression. If j1 is equal to 1, then 2j1 plus 1 is equal to 2. Similarly, 2j2 plus 1 is also equal to 2. So you have a Hilbert space H1, and the dimension of this Hilbert space is 2, and dimension of H2, this H2 is also equal to 2 in this case. So your dimension of the composite Hilbert space is equal to 2 into 2, that is 4. Now if you look at this one, okay, so let's say j is equal to 0. So j is equal to 0 means your m is equal to 0. Okay, so that means, so let me call this as HA. So you have a Hilbert space, and the dimension of Hilbert space corresponding to capital J is equal to 0 is one dimension. Now if j is equal to 1, then m can take -1, 0 and +1. So if you want to call that Hilbert space as HB, so that has a 3-dimensional space. Okay, so the same Hilbert space can now be written as, so the dimension of this composite Hilbert space can now be written as 1 plus V. Okay, so if you see that the structure of this composite Hilbert space, okay, so in terms of the Hilbert space, it is like H can be written as the direct product of H1 comma H2. Okay, and so this is 2-dimensional, this is 2-dimensional, so this is 2 into 2. Now the same H can also be represented as direct sum of these two Hilbert spaces, HA, direct sum HB, in which case this is 1 plus B. Okay, so Clebsch Gordon coefficient problem is like representing vectors in the direct product representation in terms of the direct sum representation, or direct sum representation in terms of the direct product representation. Okay, so this is one example. Now let's look at another example. So second example, let's say that we have j1 is equal to 1 and j2 is equal to, let's say, half. One is integral, one is half integral. Now what happens to 2j1 plus 1? This becomes 3. Correct? And 2j2 plus 1 is 2. So dimension of Hilbert space 1 is 3, and dimension of Hilbert space 2 is 2. So what is the dimension of the composite Hilbert space? Composite Hilbert space is 3 into 2, that's equal to 6. Okay, now what happens with respect to capital J? Capital J is equal to 1 minus half modulus 2 1 plus half. Okay, so 1 minus half is half, 1 plus half is 3 by 2, half plus 1 is 3 by 2. So you have two values for this capital J, 1 by 2 and 3 by 2. Now suppose if you take J is equal to 1 by 2, then you have M can be minus half and plus half. So dimension of HA is equal to 2 here. And if you take J is equal to 3 by 2, then M can be minus 3 by 2, minus half, half, and 3 by 2. Okay, in which case the dimension of HB is equal to 4. So if I have to write it like this, that composite Hilbert space H can be written as H1 direct product H2, and this is 3 and this is 2. Okay, and similarly I can write this as HA direct sum HB, and this is 2 plus 4. So this is equal to 6 and this is also equal to 6. Okay, it is not necessary that your direct sum representation has got only 2 spaces. It can be more spaces, because as I told you that your here this is going to be always 2 H1 cross H2, but there you can have more than 2 also. Okay, so this is just to give you how to get the total angular momentum values. Now let's try to get these coefficients. Okay, so now let me say that we'll try to find out this Clebsch Gordon coefficient. So evaluation of CG coefficient. Okay, so let us try to do it with a simple example to get a concrete understanding. And usually this is probably done in your class also. But to keep it simple, let's first consider the case of, so first let us consider the case of J1 is equal to half and J2 is equal to half. As we have seen already, now capital J is equal to 0 or 1. Now, let me write down that. So I'm going to represent basis 1. Okay, basis 1. I'm going to denote basis 1 with only M1 and M2, because this J1, J2 is common to both the bases. I'm going to represent J1, J2 with M1, M2. Now, the total, the Hilbert space is 4-dimensional, correct? Remember, dimension of composite H is 4. So I have to have 4 basis elements. Now, what are those basis elements? I'm going to write those basis elements here. They are half, 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 minus half, minus half, half, and minus half, minus half. These are the values that M1 and M2 can take, because J1 is half, M1 can be minus half or plus half, M2 can also be minus half or plus half. So these are the possible states. So this is my basis 1. Okay. Now I go back and then ask what is basis 2. Okay, so basis 2. Okay. So the basis 2 I am going to represent with only capital J and capital M, because J1 and J2 are common. So let me represent with capital J and capital M. Now this basis also should have 4 states, because dimension of H is 4. And let me say that if j can be 0, in which case m is also 0, j can be 1 and m can be minus 1, j can be 1, m can be 0, and j can be 1, m can be 1. So these are the four basis elements of second type of basis. So now our aim is to write each one of the element in the basis 2 in terms of the basis 1. That is the aim. And the corresponding coefficients are called the Clebsch Gordon coefficients. Now for that, let us use a small trick like this. Notice that there is an interesting constraint that your capital M has to be M1 plus M2, because capital M is z component of the total angular momentum. That should be equal to the quantum numbers associated with the z components of J1 and J2. So this is like a constraint. So this constraint will help us that if suppose this is not satisfied, then there will not be any relation between our corresponding Clebsch Gordon coefficient will be 0. Okay, so this helps us in calculations quite a bit. So let us use a geometrical trick like this. So what I will do is I will try to say I will represent M1 and M2 in a graph like this, and then all these four states I will geometrically represent here. So let's say this is half half, okay, half half, and this is minus half half, and this is minus half, and this is half minus half. Okay, so let's say that this is how these states are there. Okay, so now you can see that you try to connect those things geometrically that will respect this one. Suppose if I take this 1 comma 1, capital M is equal to 1, and capital M is equal to 1 will be satisfied only if M1 and M2 are plus half and plus half. So that means I can say that there is a line which I draw. This is the only line that satisfies capital M is equal to 1. Capital M is equal to 0 can be satisfied by these two things. This is M is equal to 0. And capital M is equal to minus 1 is only satisfied by this equation. So in terms of those points that satisfy given values of M, I can do like this. Now once I do this, then it is somewhat simple, because now you see capital M is equal to 1 is there only in this particular state, right? Okay, so this tells you that capital 1 comma 1, 1 comma 1 is equal to simply half comma half. That's all. This is equal to this. That means the coefficient corresponding to this is 1 and all other coefficients are 0. Okay, so you can see that there is a simplification because of this feature that capital M should be equal to M1 plus M2. Now I have to, now 1 comma 0 will have these 2 points, that is this point and this point. So in general it will be linear combination of those 2 points. So let me call that as some C1 times half minus half plus C2 times minus half half. Okay, so this is something C1 and C2 we have to determine. Okay, then 1 minus 1. 1 minus 1, once again, there is no problem because there is only one particular point. So this is nothing but minus half minus half. Okay. And this 0, 0, because m is equal to 0 here. Okay, so see m is equal to 0 here. So that is once again will be some linear combination of these two. So let me call that as some d1 times half minus half plus d2 times minus half half. Okay, so in this problem, we have to evaluate C1, C2, D1, D2. If we evaluate that, then the problem is complete. Okay, so the procedure to evaluate this one is also simple. So what we do is note the following. Note that J plus minus, these operators, can be written as J1 plus minus plus J2 plus minus. J plus minus J2. You can also write down these ladder operators of the total angular momentum as sum of the ladder operators of the individual angular momentum. Okay, so now you can see that. So what we can do now, just follow these steps a little carefully. So we will start with so to find C1 and C2. To find C1 and C2. Start with a well-known result, that is 1 comma 1 is equal to half comma half. There is no ambiguity here. Okay, and then operate J minus, operator J minus, which is equal to J1 minus plus J2 minus. So when you are doing this operation, on the left hand side you have to operate with this operator, on the right hand side you have to operate with this operator, because on the right hand side we have basis 1, on the left hand side we have basis 2. So we have J minus operator operating on 1 comma 1 is equal to J1 minus operating on half comma half plus J2 minus operator operating on half comma half. Okay, now we have to carefully look at these expressions. I have, so here I have this expression. So let me borrow this expression. So let us write that J plus minus acting on any J comma M is equal to H bar and square root of J into J plus 1 minus M into M plus 1. This is M plus minus, okay. J M plus minus 1. Correct. So this is the result. Now here I want to calculate what is j minus acting on 1 1. Okay, so that is equal to, this implies I have h bar and to square root of 1 into 1 plus 1 minus 1 into 1 minus 1, because this is j minus, and 1 comma 0. That is so this is what I have evaluated so far. Now this is equal to, now this j1 minus will act only on this one, because this is m1, and j2 minus will act only on this one. This is m2. So that is equal to, so I have h bar square root, j1 is half. Okay, so half into half plus 1 minus half into half minus 1 into, when I put j minus, this plus half becomes minus half. So this is minus half half. Plus I have a similar factor, that is half into half plus 1 minus half into half minus 1. Now I have half minus half. Okay, so now you can see that h bar will be there in all terms, so that will cancel away. And what is this? 1 minus 1 is 0, this 1 plus 1 is 2, so I have root 2 into 1 comma 0 is equal to, now here what I have, 3 by 2, 3 by 4. So I have square root of 3 by 4, and 1, this is minus half, and so I have plus 1 by 4 into minus half half, and I have same thing here, plus, so let me call this common. So I have half minus half. Okay, this is just 1, 4 by 4 is 1. So we have a result that this 1 comma 0 can be written as 1 by root 2 times half minus half plus 1 by root 2 times minus half half. Okay, so we have determined C1 and C2. So determine C1 and C2. Okay, now what is our next step? We have to determine D1 and D2. Okay, so we have to determine D1 and D2, where this 0 comma 0 is written as D1 times half minus half plus D2 times minus half half. Okay, now I cannot use any of these ladder operators to get this one, because J itself is different here. Okay, but since this has to be an orthonormal basis, so we use orthogonality. Orthogonality requirement between 0 comma 0 and 1 comma 0. So that means we require 1, 0, 0, 0 to be equal to 0. This implies I have 1 by root 2 half minus half plus 1 by root 2 minus half half. Okay, so this is my the bra vector of 1, 0, and here I have d1 half minus half plus d2 minus half half. Okay, so this has to be equal to 0. So that implies I have d1 by root 2 plus d2 by root 2 should be equal to 0. That tells you my d1 has to be equal to minus d2. Okay, d1 has to be equal to minus d2. Further, our state has to be normalized. That means modulus of d1 square plus modulus of d2 square has to be equal to 1. But d2 modulus of d1 square is same as modulus of d2 square. This implies 2 times modulus of d1 square is 1. In other words, d1 is equal to 1 by root 2. So d1 is 1 by root 2 and d2 is minus 1 by root 2. So we have 0, 0 is equal to 1 over root 2 half minus half minus 1 over root 2 minus half half. So we have completed all the determination of all the coefficients. Okay, so now you can see that we have 4 basis states in J, capital M basis, and each of this basis state is expressed in terms of M1, M2 basis, and these are the coefficients that we have determined. Okay, so this is a procedure how you try to find out any this is the simplest example, of course, but the procedure is more or less same, even if you want to do a more difficult example. Okay, so for us, for an argument's sake,
Sir,
yeah.
Sir, I have a doubt here.
Yeah.
Sir, when we say 2 spin-off particles, the
Uh,
composite dimension of Hilbert space is 4, right, sir?
yeah.
But if the particles are indistinguishable, then considering particle 1 is up plus half state, other is minus half, or other ways, and those 2 states, they are really different, they should be same, no, sir?
Yeah. So that is what I'm saying. So in that case, what happens that you can have a singlet state or a triplet state, right? So
Yes,
this
sir.
capital J is equal to, so whatever we have no here. So this
Yes,
is
sir.
a singlet state. Okay, this is a singlet state. So essentially, this is like up down minus down up by root. So this is a singlet state. Okay, your 0, 0 is basically a singlet state, and your 1, 0 is a triplet state. So you can have triplet states like this. You can have 1, 1, which is exactly, this is possible only when you have states like this. or you can have 1 minus 1. This is possible only if you have states like this. And 1 0, this is possible if you have states like up down plus down up, because this is symmetric upon exchange by root 2. Now these three states are called the triplet states, corresponding to j is equal to 1, and singlet states correspond to j is equal to 0. Correct? So this is essentially going to give you what what you get when you consider them as identical particles.
Yes, sir. But does not have any effect on dimension, sir, because mm, sir,
Effect
if
on dimension of what?
dimension of the composite Hilbert space, this identicalness.
It is there. That is essentially, see, it is because of that you are able to get this direct sum structure, no?
I didn't get, sir. Can you explain?
That is, whatever 2 cross 2 is 4, and this
Yes,
can
sir.
be realized as 1 plus 3 is equal to 4, right? So this is
Yes,
singlet and this is triplet.
yes, sir.
So this direct product to direct sum structure is there, no? The
Yes,
structure
sir.
is the total Hilbert space is same, but then it can be decomposed as a direct sum of. In other words, it is like suppose if you are writing a matrix, okay?
Yes, sir.
If you are writing a matrix, that matrix will have a block diagonal structure where
Yes,
you
sir.
have 1 by 1 block and 3 by 3 block. And 1 by 1 block is for the singlet and 3 by 3 block is for the triplet.
Okay. Yes, sir.
The
Yes, sir.
direct sum structure is like a block diagonal structure of the matrix.
Yes, sir. Okay,
Like
sir.
in the previous case, we talked about 1.5. In that case, you have a 2 by 2 block and a 4 by 4 block in a 6 by 6 matrix.
Oh, yes, sir.
Okay, that kind of a block diagonal form, it will be there.
Yes, sir. Sir, this is related to that what you have taught us before, this commutability up to observables. Like same
Right.
way we can relate.
Correct. So this is because we are here, CSCO is there, no? So we have CSCO, different CSCO are there.
Yes, sir. Yes, sir. So, okay.
Okay. So I think if you want to fix your ideas, maybe we can look at one more example. Suppose, let's say that you want to find out uh, J1 is equal to 1 and J2 is equal to half. So in which case we have seen that J can take values half and 3 by 2. Okay, so this is dimension of Hilbert space 1 is 3, and dimension of Hilbert space 2 is 2, and dimension of composite Hilbert space is 6. And here you have, this is 2-dimensional and this is 4-dimensional. So the 6 can be written as 2 plus 4. Okay, so now you have 6. So let us try to write this. Basis 1. Okay, so basis 1. How do we write basis 1? We have to write down 6 elements, correct? So that is our M1, M2 basis. M1, comma, M2 basis. Okay, so first one can be 1, second one is half, and first one can be 1, second one can be minus half. And this can be 0, this is half, and 0 minus half. And this is minus 1, half, minus 1, minus half. So these are the 6 possible basis 1 states. Now let's write basis 2 states. Now basis 2 is JM states. Okay, so these are JM states. Now capital J can be half. So capital J can be half and M can be minus half, or it can be half. Okay, let's write this as plus half, or it can be minus half. These are the two possible states with capital J equal to half. Otherwise, capital J 3 by 2, M as 3 by 2, capital J 3 by 2, M as 1 by 2, capital J 3 by 2, M as minus 3 minus half, and capital J 3 by 2 and capital M as minus 3 by 2. So these are the 6 states associated with JM basis. Now, like in the previous case, we can simplify our analysis by drawing this graph. So let's say I'm going to draw this graph with my M1 and M2. Now you can see that M1 is equal to 1, 0 and minus 1. So I can have this is like minus 1 and 0 and plus 1. This whole thing is with half. And similarly, I can have with a minus half, 0 and minus 1. So this is like this is like 1 comma half. This is like 0 comma half, and this is like minus 1 comma half, and this is like so this is like minus 1 comma minus half. Okay, sorry, 1 comma minus half, 0 comma minus half, and minus 1 comma minus half. So this is these are the things that I am representing basis 1. Now we will use this fact that capital M has to be equal to M1 plus M2. Okay, so now you can see that when I want 3 by 2, capital M is equal to 3 by 2. That means I want this state. Okay, this state is possible only with this one. Correct. So let me now write down this one is corresponding to capital M is equal to 3 by 2. Okay, 0 plus R or 1 minus half. Okay, so these two will be capital M is equal to half, and these two will correspond to capital M is equal to minus half, and this will be capital M is equal to minus 3 by 2. So now you can see that among all these six different values, so let me now just look at what can be directly written. For example, I can directly write 3 by 2 comma 3 by 2 is simply 1 half, because there is only one particular point here. So there is only one particular point. Similarly, I can write down 3 by 2 minus 3 by 2 as minus 1 minus half, because even this particular point there is only one. So these, in the other cases, there are two different points. So what are they? For example, suppose I want 3 by 2 and half. Okay, so 3 by 2 half is like so let's say some C1 times 1 comma minus half plus C2 times 0 comma half. Okay, this is what it is. Now this also, the same particular thing, we can also have half comma half. So half comma half is equal to let us say some d1 times 1 minus half plus d2 times 0 comma half. Okay, so C1, C2, D1, D2 correspond to this particular. Now you have two more. Okay, what are they? That is 3 by 2 minus half is equal to, so maybe let me call it as C1 prime times, you have 0 minus half plus C2 prime times minus 1 plus half. Then I have half minus half is equal to d1 prime. Let me call it as d1 prime okay, d1 prime 0 minus half plus d2 prime minus 1 half. So now you can see that I have to evaluate these 8 coefficients. Now evaluation of these 8 coefficients is again the procedure is same. So what I will do is that to find C1 comma C2, start with 3 by 2 3 by 2 is equal to 1 comma half, and operate j minus, which is equal to j1 minus plus j2 minus. Okay, so we have 3 by 2 3 by 2 is equal to 1 comma half. Okay, so now j minus acting on 3 by 2 3 by 2 is equal to j1 minus acting on 1 comma half plus j2 minus acting on 1 comma half. As usual, this j1 minus will act on this and j2 minus will act on this. So that is equal to, I have h bar and square root of 3 by 2 into 3 by 2 plus 1 minus 3 by 2 into 3 by 2 minus 1 into 3 by 2 half. That is the left hand side. Now h bar square root of 1 into 1 plus 1 minus half into half minus 1 into 0 comma half plus h bar square root half into half plus 1 minus half into half minus 1 into 1 minus half. Okay, So this is so now you can see that 3 by 2 plus 1 is 5 by 2. 5 into 3 is 15 by 4. So I have 15 by 4. 3 by 2 minus 1 is 1 by 2. So 15 by 4 minus 3 by 4. That is 12 by 4, which is equal to 3. Okay, so I think I have root 3 into 3 by 2, 1 by 2 is equal to, this is 2. So square root of 2 minus, the half minus 1 is minus half. So 2 plus 1 by 4. Okay. 0 comma half. Plus this is 1. Correct. This is 1 by 4, 3 by 4 plus 1 by 4. This is 1. That is 1 minus half. Okay, so this is 9 by 4. So that is equal to 3 by 2. 0 comma half plus 1 minus half. So we have 3 by 2 comma 1 by 2 is equal to 1 by 2 root 3, 0 comma half plus 1 by root 3 . Okay, just a minute. So we want to say plus 1 minus half. Sorry. So here I have to act on this. So this is actually 1 only. 1 into 1 minus 1. Because m is, this is m1, right? m1. So it is not half. So this will not contribute. So this will be simply root 2. So this is root 2 by 3. Okay. So now you can see that I have C1. I do not know which one I called it. Okay, that's 1 minus 1, I think yeah. 1 minus half I called it as C1 and 0 half I called it as C2. So my C1 is equal to 1 by root 3 and C2 is equal to root 2 by 3. Okay. Now to find D1 and D2, we use orthogonality and normalization. Okay. Now, if you want orthogonality, it is always can do it, but it is very easy to see that. So you want 3 by 2 half and half to be 0. This implies your D1 is equal to C2 and D2 is equal to minus C1. Okay, you have to swap and then put a minus sign. That's so that you get the inner product to be 0. So you have half comma half is equal to you have root 2 by 3, 1 comma minus half minus 1 by root 3 into 0 comma half. Okay, So I have evaluated E1 and E2. Now what to do for getting uh, the next one? That is, so up to this we have evaluated. Now to get this one, to get 3 by 2 minus half, you can actually put a j minus on this. But then that is going to be a little complicated because you have to evaluate 4 terms on the right hand side. So it is always, you should choose the simple one. Okay, so to find T1 prime, T2 prime, okay, you start with 3 by 2 minus 3 by 2 is equal to minus 1 minus half. And then operate j plus, which is equal to j1 plus j2 plus. Okay, so why I am saying this is better, because you can just raise this one. So now you ask what is j plus acting on 3 by 2 minus 3 by 2. That's equal to j1 plus acting on minus half, minus 1 minus half, plus j2 plus acting on minus 1 minus half. Okay, so you can write this. So this is equal to h cross square root of 3 by 2 into 3 by 2 plus 1 minus, you have m is equal to minus 3 by 2 here. So that is plus 3 by 2 into minus 3 by 2 plus 1 into 3 by 2 minus half. So that is plus 1, right? So that is equal to h bar square root of 1 into 1 plus 1 plus 1 into minus 1 minus 1 plus 1 into minus 1, sorry, this will become 0 minus half plus h bar into square root of half into half plus 1 plus half into minus half plus 1 into minus 1 half. Okay, so this is, I request you to simplify this. You get these coefficients, and then to find D1 prime and D2 prime, use this fact that your 3 by 2 to minus 1 by 2 with half minus half, that should be orthogonal. That means you once again swap and then put a minus sign. Then you will have these coefficients. Okay, so this is how you have to evaluate these coefficients. Okay, so there are many interesting results. I mean, places where you require to use this. For example, let's say that let's say that you have okay, let's consider some kind of a hydrogen atom kind of a problem, or any other atom problem. So there is something called so you have this stationary states stationary states of let's say hydrogen atom. Okay, so they are in terms of these quantum numbers n, l, and m. Okay, you have this n, l, and m, or you can say that n, l. Okay, so let me put it more generally: n, l, m, s, and ms. If you have a spin, then you have. So if you look at this part, you forget about L, but this part is like our. This is like basis 1. Correct? You have M and MS. This is like basis 1. But suppose if you have some perturbation. Okay, so think of perturbation due to something called the spin orbit coupling. Okay, spin orbit coupling. That means this is a relativistic correction. If you are looking from the frame of reference where the nucleus is at rest, then where the electron is at rest, then the nucleus will be going around this electron, and that constitutes a magnetic field with which the electron spin can interact. So typically, the Hamiltonian corresponding to the spin orbit coupling, if you want to write a perturbation Hamiltonian, that will be some constant times you will have L dot S. Okay, so this is the form of the spin orbit coupling. Okay, spin orbit coupling Hamiltonian. So if you have something like this, then let's say you are interested in, now you are finding that the observed spectra has got some change. That means the spectral frequencies are different, or they are splitting, something like that, or the energies or the frequency is not same as what you are observing. Then you would like to calculate change in the energy levels because of this spin orbit coupling. That means you would like to calculate, let's say, first order correction. First order correction for energy. For energy is given by some NLM and then this H prime SO. This is the perturbation Hamiltonian, and NLM. Okay, this is the expression from the perturbation theory. You can see that this is the expression. But now notice that this N, L, M are not eigenstates of this L dot S. Okay, these are not eigenstates of this L dot S. So it is necessary to establish, write this NLM in terms of the eigenstate of this L dot S. Like you can see that, so I can say that L plus S is the total angular momentum, and then this square of this one is that is your J square. Okay, so J square is equal to L plus S square, which is nothing but L square plus S square plus 2 times L dot S. So from here I can write down this L dot S to be J square minus L square minus S square divided by 2. Okay, now if you see that this NLM are eigenstates of L square and S square, but they are not eigenstates of J square. Okay, but if you have eigenstates of L square, S square, and J square, then that will be an eigenstate of L dot S. So if you write down this NLM in terms of the eigenstates of J, you have to represent this NLM using Clebsch Gordon coefficients. If you can write that, then you can construct a state that is an eigenstate of this L dot S operator, and then the first order correction to the energy can be easily calculated. So this is one application that I can immediately think of, and this spin orbit coupling is very important in nuclear physics. When you do shell model, etc., the spin orbit coupling is what gives rise to correct energies and correct shift in the energies, and the shell model is completely based on corrections due to spin orbit coupling. Okay, so this is one simple example where the Clebsch Gordon coefficients are very important. If you can write these things in terms of Clebsch Gordon coefficients, then you can directly get the perturbation energies calculated. Okay, so maybe I will stop here. If you have some questions, you can ask. But know if whatever I did is clear.
Sir, we consider that N is not in the eigenbasis because it was hydrogen atom only, right, sir?
Yeah, N is for our discussion. N is not important, but it is only LS and then capital J.
Yes.
That is our J1, J2, and capital J, capital N. That basis.
Yes. So if we are considering atoms with higher quantum means higher orbitals, then we should consider N also to represent this basis.
N is like it is representing the energy of the system.
Yes, sir.
Yeah. So that comes because of you are considering a potential and then solving the radial equation. So that N comes from there. Okay. So, but here, as far as angular momentum is concerned, when you change it from LS basis to J basis, that N will not get affected.
Yes, sir. Yes, sir. That's correct, sir.
Yeah.
Sir?
Yeah.
Sir, this case, this spin orbit coupling term, that correction to the Hamiltonian we treat as a perturbation, right? In the non-relativistic case. But sir, relativistic case, it comes out naturally, no? We need not to put that term H plus that perturbation term or what?
Yeah, if you are solving hydrogen atom problem using Dirac equation, then it is there in that.
Yes, sir.
So everything is there in that.
Sir, there will be another term also while in perturbation theory I have seen that correction to the kinetic energy term, relativistic correction. That
Correct,
also
correct. Yeah. That also will be a part of Dirac equation. But then here you have to, that is, if you are trying to write down from E square equal to P square C square plus M square C power 4, from that equation, if you are writing an expression for kinetic energy, your first term is P square by 2M. But
Yes,
suppose you keep one more term, then that is that P power 4 term will come.
Okay.
That will give rise to some fine structure in your spectral lines.
Yes, sir.
Okay, that part, all the in fact, if you solve Dirac equation, all powers will be there in that.
Yes, sir. But here we consider up to P4, first term only, sir.
Correct. That is because see that Sommerfeld had made all these relativistic corrections to explain the observed spectra.
Yes, sir.
The Dirac equation is a kind of a fully relativistic treatment, and once you get energy levels of the Dirac equation, that will be final. but you can also look at different limits of non-relativistic corrections and get all these terms as a part of non-relativistic limit of the Dirac equation.
Yes. Sir, one video you have shared now in Sunday Physics, Lena Susskind, that time. In that, sir, in the beginning, he says, no, Dirac way of doing theory, look for beautiful equations.
Yeah.
Yes. Sir,
Yeah,
sometimes
it was good. I've shared that. I think I've shared it in this class also. I
Yes,
wanted
sir.
you to notice that the final statement that he makes is
Yes,
that the issue of arrow of time
Yes, sir.
is not understood.
Yes, sir. Yes, sir. I have seen, sir. Sir, is very nicely simple things that horizon, how universe is expanding. This thing he put it very simply, very nice.
Yeah.
Yes, sir. Thank you, sir.
Yeah.
Sir, this relativistic quantum mechanics sometimes, sir, can you teach? Time is there.
Yeah,
Thank
we
you.
will do it in some forum. We will do it.
Yes, sir. Yes, sir. At least, yes.
If anyway, these things are somehow meant for some. These are meant towards some exams or something. So, from the examination point of view, that is not important, but that is very important for learning.
Yes, sir. Okay, sir. Thank you, sir.
Yeah. Okay. Any other question? So I think some of you said this addition of angular momentum was was not done, or you have not learned it earlier. So is this clear now?
No, sir, it is very clear, sir. I wanted to say that I was struggling with this, but it is very clear now, sir. Thank you very much, sir.
Okay. What about Debanjan? I think you also had.
Yes, sir. Now it's clear, sir.
Clear? Okay.
Yes.
Okay, so I think if it is fine, we can close it. There is one thing which is related to this. It's called Wigner-Eckart theorem. Okay, so Wigner-Eckart theorem is a general theorem which will try to write down the expectation value of some spherical tensor operators are decomposed in terms of some Clebsch Gordon coefficients, and then an angular momentum will be added. So there is a very general theorem, and sometime when you get time, or if you want to learn a little more, try to read something on Wigner-Eckart's theorem.
Okay, sir.
Yeah.
Sir, it is Wigner. Can you spell it, sir?
Wigner-Eckart. Wigner. Wigner. Eckart. Eckart. Wigner-Eckart theorem.
Yes, sir.
Okay, so then we will close. Ashley, we'll close.
Yes, sir. Sir. Thank you, sir, and good night, sir. See you.
Good night.
Thank you,
Bye.
sir. Good night, sir.
Good night. Bye.